Okay, team, Dave is here to talk about mass timber. This is a lecture, you've given this for woodworks, you've given this for a few
NORAD.
For a few different companies. You're giving it twice, I think, to 2 different companies in the next month. So it isn't similar to mine last week. It's not following like a normal kind of here's the information as a student, but more as a here's information as a person out in the world building stuff. He has to use my computer, so I can't work while he's filming this, so I'll be kind of lurking and puttering around in the background, offering color commentary.
Oh, great. I love that.
And so you just have to bring this over, stop recording, you're all set.
Driving with the driver's ed instructor beside you. Okay. Okay, so the title of this lecture is What's the Deal with Mass Timber? Everybody is talking about mass timber, and yet it's hard to know exactly why you would do it, and where it fits in the industry. Are there advantages, are there disadvantages, and how do we work with it? And it is not a simple topic. It is a complicated thing. Wood is the most complicated of the building materials to work with, structurally, from a fire point of view, acoustically. So let's talk about it. And is it a fashion, or is there actual value in building with mass timber? So the first thing we need to do is try and understand what is mass timber. In order to understand what mass timber is, we have to understand what heavy timber is. Heavy timber is distinct from a regular wood frame because its fire performance is better, and because its fire performance is better, we can use it in larger buildings. The NBCC that's the National Building Code of Canada, defines heavy timber as wood elements in heavy timber construction shall be arranged in heavy solid masses with essentially smooth flat surfaces to avoid thin sections and sharp projections. This is the characteristic of heavy timber that makes it more fire safe, and we'll talk about fire safety a little bit more later. The explicit definition, columns have to be a minimum of 140 millimeters, beams have to be a minimum of 89 millimeters, floor decks, minimum 64, roof decks 38, and if you meet these minimum dimensional requirements, you're deemed to have a 45-minute fire rating by default. So, I mean, as you know, what that means is that the building will maintain its structural integrity for 45 minutes after the onset of a fire, which allows the occupants a chance to exit the building. So what is mass timber then? Well, mass timber has no definition in the National Building Code. It is essentially a building system comprising larger engineered elements manufactured by assembling smaller pieces of sawn or peeled wood using adhesives or mechanical fasteners. Fire resistance of mass timber elements are calculated in accordance with NBCC Appendix D. Essentially what that does is allows you to calculate the burn rate of the wood and estimate the remaining core after your fire duration and evaluate the structural capacity at the end of your design fire. BC Building Code did just add a mass timber definition. The mass timber definition is essentially the same as the heavy timber definition, except that the sizes are rounded to suit dimensions of standard glulam, CLT, and LT panels. But otherwise, it's a very similar definition to heavy timber. So let's look at some of the drawbacks of using wood, or some of the perceived drawbacks of using wood. Fire is the number one. So people perceive that because wood is combustible, therefore it's not fire safe, and it's simply an erroneous presumption. Anybody who's tried to build a campfire, or even a fire in a fireplace, knows that fire will not sustain combustion in the absence of a re-radiating surface. So that's a wonderful quote by my pal Steve Kraft from CHM Fire. Essentially what that means is if you have a log on its own, you cannot light that thing on fire. The only way you can get that to light on fire, you can put two logs side by side so there's a gap, it'll catch fire in the gap. You can put it adjacent to the back of your fireplace, it'll catch fire in a gap, something. But it needs a re-radiating surface to sustain combustion. If you look in the background of this slide here, you can see that where it's burning is up near the top. It's the wall and roof intersection where the fire can radiate in the corner is where it's susceptible for combustion. It doesn't burn on the flat surface. Actually, I'm going to come back here. One of the things that makes wood fire safe is that the char, this black layer on the outside, is an insulator. So as it chars, the char layer protects the core and protects the, and the thicker the char layer, the more insulation, the slower the progression of heat into the wood. Generally, we think of the progression of development of char taking place at about 41 millimeters per hour. So we can say in very simple terms that wood exposed to a design fire for an hour will lose 41 millimeters on all exposed surfaces. So that might be two sides and the bottom because the top might have a deck on it. But we know then what's left in the middle, and what's left in the middle still has structural integrity. So that in very simple terms is how we would design for fire. It's a little more complicated than that because we don't need the building to sustain full service loads in the event of a fire. We need to sustain, so we don't need full safety factors and we don't need full service loads. So we use reduced loads in the event of that fire load case. And this is a wonderful picture. This is from I think from the Great San Francisco Fire at the turn of the 19th century, turn of the 20th century, post-earthquake. And what we can see is that the steel elements have failed. They turn to spaghetti in the presence of heat. They have a dramatic loss of strength and stiffness. The wood element certainly charred, but that solid core was left in the middle, and so the wood element stayed intact and is supporting the failed steel elements. This is a photo from the Triangle Shirtwaist Factory Fire in 1911, one of the worst fires in American history. Something like 140 people died in this fire. So tremendous loss of life, extremely tragic. All of the loss of life was related to fire code violations. There was a fire escape that was on the side of the building. It collapsed. There were doors that were barred to prevent people from leaving and taking breaks. But the structure did exactly what the structure was supposed to do. So here's a mass timber building that is completely intact following the fire. So we know that mass timber and heavy timber are fire safe. And I should actually just say, so why does wood have a bad rep? Light wood framing is not fire safe. So light wood framing, you have thin elements, you have them relatively closely spaced. So there's all these re-radiating cavities between joists and within stud walls are really the worst possible situation for fire, which is why when we build with light wood framing, it's suitable for single family homes because you're never far from an exit in most single family homes. Multi-story buildings up to 6 stories, but there the fire protection requirements are stringent. So mandatory sprinklers, multiple layers of drywall to provide insulation to the wood. So light wood frame needs to be fire protected. Mass timber doesn't necessarily. Another major concern people have about building with wood is water. And to be sure, wood is vulnerable to decay in the presence of water. But it's not vulnerable to decay if it's taken care of properly. So the decay requires liquid water for decay. This little graph here shows you, well, I should say that fungal growth happens when the moisture content of the wood exceeds about 25%. If we look at this graph and we compare relative humidity of air and temperature, what we can see is that the moisture content of wood.
Here's food if you want it.
Thank you.
I don't know if you dare. With that fine mustache, I don't know if you dare to eat food while giving the lecture or not. But there's food for you.
I'm gonna have a shredded cheddar cheese mustache. This is the normal condition of the building, 22 degrees Celsius, 50% relative humidity, and we have a 9.5% moisture content. Let's see what it takes to get up to 25%. We need low air temperature and moisture content, or a relative humidity, very, very close to 100%. And it needs to be sustained. It's not like as soon as you hit 100%, you've got 25% moisture content. It takes a long time for wood to absorb moisture and to raise the moisture content. So you need sustained conditions of very, very high humidity in order to bring the moisture content up high enough for fungal growth. Which means that really you need liquid water. In fact, when we're doing pools, we'll often use a wood deck, even if it's not exposed to view, simply because the wood is, the longevity of the wood is so good in that extremely wet environment, as opposed to a steel deck. If the steel deck in a very high humidity environment doesn't have to be much below room temperature to drop below the dew point, and you get condensation, and a steel deck will start to rust in a relatively short period of time in a pool. So really we need liquid water. So wood is vulnerable and needs to be protected by your building envelope. You got to maintain your roofing intact. You need proper flashings. It needs to be prevented from accidental wetting due to long-term plumbing leaks. A dripping toilet or a leaky dishwasher, or those are the kinds of things that will shorten the life of a wood.
All things we have in our house.
Yeah, we got both. All things that will shorten the life of a wood structure. What about cost? Well, anecdotally, wood structures are generally considered to be about 15% more expensive than the comparable steel or concrete structure. But of course, there is a gigantic range. Many of the precedent projects that we're going to see, the wood structure is twice as much as the comparable steel or concrete structure, simply because the choice of using wood was made on aesthetic reasons, and the wood structures were designed explicitly to be expressed, and you're comparing them to a kind of meat and potato steel or concrete structure. And if we look at this NRC report commissioned, or Hanscom report commissioned by the National Research Council, we see a different story. So this was a 12-story building, office building. It was designed in 4 different ways. It was designed as mass timber, encapsulated mass timber, which means covered in drywall for fire protection, concrete, and steel. And what we can see is that the mass timber structure is actually the least expensive of the 4 alternatives, because the mass timber structure in this study was optimized. Now you don't always have, the mass timber structure in this study probably had a 6 meter by 6 meter span, for example, because that's optimal for mass timber. It's not optimal for a 12-story office building. So it can be very economical if it's used in its optimal way. And anecdotally, as I say, generally it's considered to be about 15% more expensive than concrete or steel buildings. That is 15% more expensive on 20% of the building. So about 3% premium on the building cost. So what about strength? I love this image, not only because of the cool old-timey strongman on the right, but the strength density diagram is so telling. This is, we take strength divided by the density. So that's how much strength is there in 1 kilogram of the material, regardless of the volume that 1 kilogram takes up. So you benefit your lighter materials because you're acknowledging they're lighter. You've just taken a certain amount of material, you've expanded into a larger volume. What we see when we compare strength density is that concrete is way down here. Hardwood is here. Softwood is up here very close to steel. Strength and stiffness density as well. So we take the elastic modulus divided by the weight, and we get a very similar story. So softwoods are comparable to steel in strength density, which means that if you build a building out of wood and you build a building out of steel, the two are going to weigh about the same. That is, that the weight of material, the weight of a wood beam that replaces a steel beam will weigh about as much as the steel beam. It'll be bigger because wood is so much lighter and so much less dense, but it weighs about the same. And the concrete beam will be much heavier. This is a bit surprising. Here we see that the hardwood is not as good as the softwood, and we perceive hardwood as being a better wood. It is a better wood, but one of the things that makes it better is its density. So hardwoods are much more dense than softwoods. The strength density is actually less. They are denser than they are stronger, if that makes sense. So let's think about building codes. The building code currently allows light wood frame buildings up to 6 stories, which was a big change in 2015 building code. So 6 stories is a limit. Makes no exceptions for mass timber. And yet we've got projects like this underway. 77 Wade, 100,000 square foot, 8-story office building, has approvals in place. U of T Tower is a 14-story office building, which has just received the planning approval. We don't have a building permit, but we have approval. So to move to the next stage now, because the way that these buildings get their approval is through an alternative solution. The building code has prescriptive measures that says you can build this type of building this big, but there is a provision in the building code for alternative solutions that says that if you can demonstrate that you meet all the intent of the prescriptive measures, you are not bound by the prescriptive measures. So these projects have gone through an alternative solution process to demonstrate that they are at least equal to the building that would have been prescriptively allowed, in terms of, primarily fire safety, but fire safety, durability, structure. So we're not really limited by the building code. The building code provides limits, but it also provides an out. So OBC 2012 allowed 6-story wood frame. The NBCC 2020 is projecting 12-story encapsulated mass timber. So we will be permitted by code to build up to 12 stories in mass timber. That's encapsulated, so it has to be covered in drywall, but it's not 100% encapsulated. So we can express and expose a certain amount. But as I said, these two buildings here are largely exposed mass timber. They're not considered encapsulated mass timber buildings. and they've got the approvals in place. The IBC, which is the International Building Code, this is the one the Americans use, are projecting 18-story encapsulated mass timber by 2021. 12-story partially exposed mass timber, so they're more liberal than us in that at the 12-story as well. And the IBC will allow 8-story fully exposed mass timber by rights in 2021. So, are there any benefits? We know that the drawbacks, the perceived drawbacks of building with wood are generally not that valid, but are there benefits to building with wood? The major benefit to building with wood, of course, is sustainability. Whereas building with concrete and concrete and steel results in a great deal of new CO2 in the atmosphere. Building with wood actually encapsulates CO2. It's carbon negative for the structure. The approximate rule of thumb is that 1 ton of carbon is encapsulated. 1 cubic meter of mass timber or wood used in construction encapsulates as much carbon as is contained in 1 ton of CO2. Did I say that right? 1 cubic meter of wood encapsulates as much carbon as is contained in 1 ton of CO2. This was always a very confusing statistic for me because 1 cubic meter of wood doesn't weigh 1 ton, so how can it encapsulate 1 ton of carbon? It doesn't encapsulate 1 ton of carbon. It encapsulates the carbon that would have been in 1 ton of CO2, and then the O2 is released into the atmosphere where it's harmless, or beneficial in fact. One environment industry magazine quoted, "The best thing to do is to preserve the forest through responsible management while harvesting as much wood as sustainable for production of construction products." So what we're doing is there is a truism that at end of life, if wood is then either burned or allowed to rot or compost, then you are restoring that CO2 to the atmosphere. So that carbon becomes CO2 when it's back into the atmosphere. But if we can take that carbon out of the atmosphere for 100 years, then that is a benefit. And as long as we're accelerating the use of wood, it's as though we have a permanent carbon sink. Some interesting statistics on sustainability. If we follow the loose fit, long life, low energy philosophy of building, we find following the loose fit, long life, low energy philosophy of building can dramatically extend the life of a building. And a study in Minneapolis found that at the time they were demolished, wood buildings were an average of 75 years or greater in age, whereas concrete and steel buildings were less than 50 years. The reason is not because wood lasts longer explicitly. We can design a concrete building to last 500 years. We can design a wood building to last 500 years. It's that these wood buildings were designed in a very, I don't want to say a generic way, but in a way that allowed multiple lives for the buildings. And we see this in Toronto so much. These buildings in the garment district were built for manufacturing in the late 1800s, early 1900s. but then have gone through multiple lives, have become residential buildings, have become office buildings. And the reason is because they were a very standard 16-foot square span, flat floors, good floor-to-floor heights. They were buildings that could be adapted to many, many different things. And the fact that people like being in wood buildings has just meant they've always had appeal as they change their use. One of the real benefits of wood is that it's not concrete. We have a very uncomfortable relationship with concrete. Concrete Saskatchewan says concrete is versatile, long-lasting, durable, a cost-effective, and sustainable choice. The Guardian calls concrete the most destructive material on Earth. Concrete is not modest amounts of concrete are not going to hurt anybody in construction. The trouble with concrete is that it is the best construction material. It's fire safe. And Shannon's talked about this in her lectures, but it's fire safe. It's massive. It's not. It's rigid, so we don't have vibration problems. It provides a good acoustic barrier. It's very flexible and versatile, and for all those reasons, it is utterly ubiquitous. And we build so much in concrete, and that's really the problem. It's not that there is anything explicitly wrong with concrete. It's just that when you're building so much concrete continuously, that it becomes a problem. So what are the problems with concrete? Well, one is obviously CO2. The concrete industry is responsible for something like 8% of the total global CO2 emissions worldwide. So it's just a gigantic contributor to greenhouse gases. This is the production of cement is an extremely energy intensive process. So just backing up a little bit, concrete consists of gravel, sand, water, and cement. And the cement is the binder, so it's a critical part of the concrete. You can't have concrete without cement. Cement is extremely energy intensive to produce. It requires an awful lot of heat, and that's what makes concrete such a terrible contributor to greenhouse gases. Sand is another problem. We build enough in concrete to build a wall 80 feet tall and 80 feet thick around the equator every year. We build with an astonishing amount of concrete. One of the major problems is the world is running out of sand. It sounds crazy, but you need a certain type of sand to build for construction. It needs to be sharp-edged sand. It needs to interlock. The round sand from the desert that's wind-worn is not good for construction. It doesn't bind well enough. So we need water sand, which means we're dredging harbors and dredging rivers and dredging oceans to harvest sand. We're tearing up beaches, and there are literally worldwide sand cartels. There's organized crime in the sand business that are sneaking in and excavating sand from beaches in the night, and people are killed for sand. So sand is a huge problem. In the Middle East, they are importing sand by the container load, or by the truck, by the container ship load from Australia. You can imagine moving sand halfway around the world in the Middle East, where you picture being nothing but sand. So sand is a gigantic problem. And we don't think of it in Canada because we have sand, and so it's not a problem for us. Another problem with concrete is silicosis. Silicosis is a chronic, non-malignant lung disease caused by the inhalation dust of silica, which is a mineral that's part of sand and rocks and mineral ores. So basically, If you are working in concrete, you are inhaling silica dust, and it's damaging your lungs. So people who work in the quarries, people who work in the manufacture of cement, and even people who are working on job sites are vulnerable to chronic lung disease. And we think of wood as generating dust because we can picture sawdust so easily. You cut a piece of wood and you've got dust. The major difference is that the dust particles generated by cutting wood are large, and so they don't become very fine airborne dust in the same way that silica dust does, and so it doesn't have the same impact on our lungs. I mean, to be sure, if we breathe enough sawdust, it's problematic for our lungs, but because the particles are large, it's not the same kind of problem. The other thing is mass timber. The fabrication happens off-site. It happens in a manufacturing facility where there would be dust capture, and so it's a relatively clean environment. So a benefit to wood construction is that it's fast, clean, quiet, and warm. So it's fast because everything is prefabricated off-site. So you're not constructing, you're assembling. All the construction has already happened. You're bringing completed pieces together and assembling them. This is an image from Brock Commons. Brock Commons, 18-story building, was erected in 45 days. So astonishingly fast. It's an optimized project. I mean, things have to be optimized if you want them to be fast. It's quiet. It's a quieter way to build. We can think, oh, saws and drills and things, they sound loud, but they are not loud compared to the construction processes associated with concrete, for example. It's clean. As I say, the manufacture happens off-site, so wood construction is generally just assembly, so it's a clean way to build. And it's warm. This is an interesting one, because why would wood be warmer? It's an outdoor environment until it's enclosed, and then it's enclosed and it's a conditioned environment. But wood is, it has a low conductivity and a lower heat capacity than concrete, for example. So you don't get a radiant cooling effect. Now, radiant cooling is one of those things you say, well, I mean, radiant cooling is obviously a fiction. You can't have radiant cooling. What radiant cooling is the failure to re-radiate back your heat, which again sounds like why is that an issue? It doesn't sound like a real issue, but if you've ever sat next to a window in the winter, you realize how much of your body heat, which is lost through radiation, gets reflected back off the surfaces around you. All the surfaces that feel warm are reflecting back the heat that you're losing. The surfaces that feel cold when you're close to them are not reflecting back that heat. So concrete is absorbing the heat where wood is reflecting it back, and it creates a warmer environment to be in. I was just listening to something recently that is utterly counterintuitive. That in the desert, in the outside of the shaded areas, the ground temperature is colder than the air temperature overnight. And the reason is that in addition to being cooled by the air, the ground is radiating heat, which is lost into space. Under a tree, it's equal to the air temperature because the heat is being re-radiated back. Wood structures are associated with wellness. So there have been studies that have demonstrated in wood buildings increased productivity, reduced absenteeism, and happier people. To be sure, these studies may have had an agenda. It's unlikely that the findings were actually false, but someone found what they went looking for in these studies. But they're not incorrect. Biophilia is the urge to affiliate with other forms of life. So this is the the effect that we're seeing when people working in wood buildings. So the studies have shown lower stress, lower blood pressure, lower heart rate. If you can imagine that people in wood buildings have been found that their heart beats 3,500 fewer times per day. So 45 minutes worth of heartbeats are saved working in a wood building. The presence of wood suppresses the sympathetic nervous system, which is the fight or flight nervous system, and reduces cortisol levels in the blood. So generally, people prefer being in wood buildings. Wood is a hygric mass. So hygric is the ability to absorb and re-radiate water. And we can call this the humidity flywheel effect. So wood absorbs and releases moisture to maintain the indoor environment within an optimal range. Wood that's exposed on the inside. And this is one of the reasons why wood is so good in a wet environment. Say that you do get some condensation in the ceiling of your pool. Well, wood has the ability for local moisture to absorb that moisture within the wood, distributed within wood through the capillary the cells, so that the moisture content is left below 25%, except very locally, even in the presence of some amount of liquid water. So wood is effective at helping to maintain the indoor environment through the humidity flywheel effect. It's also a tremendous thermal mass. Concrete is always credited with being such a great thermal mass, and it is. What is not intuitive is that the thermal mass of concrete is 0.875 kilojoules per kilogram degree Kelvin. The thermal mass of wood is about an eighth more than that. So the thermal mass of wood is actually higher than concrete. The reason we don't think of wood as a tremendous thermal mass is, first of all, its weight is only about 25% of concrete. So much less weight means that even though the thermal mass per kilogram is higher, the thermal mass per cubic meter is quite a bit lower than concrete. The second is that wood is much less conductive, which means that the stored thermal energy is not accessible as quickly. So if a concrete floor cools overnight, then the next day the floor is cooling the environment, and or conversely, if it warms up in the sun during the day, then you have access to that heat that night when the sun's not there, and the concrete is re-radiating it. Wood being less thermally conductive, you don't have access to the heat in the same way. But for a long-term flattening of the temperature curve, wood is effective. And mass timber, notwithstanding that it's much lighter than concrete, in a mass timber panel, there is quite a bit of it. So a 10-inch mass timber panel would have a thermal mass of a 3-inch concrete topping, and so not insignificant. What about money? Well, commercial landlords have recorded higher rents, better tenants, and shorter vacancy periods in their wood buildings. Atlantic, which is Toronto's first mass timber commercial building in 100 years, the building did not meet the pro forma of the building, and yet it's still been, in terms of square footage on the site, has still been tremendously successful for the landlord. what constraints do we have to keep in mind? Well, vibration and acoustics. So Steve Titus gave me this quote, wood benefits from the effects of psychoacoustic perception, which means that because we associate wood with a warm environment, we assume that it's going to be acoustically perform well. It doesn't. Wood is actually slightly more reflective than concrete. Here's our noise reduction coefficient for wood. Here's our noise reduction coefficient for concrete unpainted. So wood is not acoustically absorptive. It is reflective, and in fact, one of the major barriers for exposing wood in mass timber buildings is exactly that. We need the absorptive surfaces. We wind up covering a lot of the wood with acoustically absorbent panels. We can mitigate the sound reflection, but we do it by adding something, and we can add something that is made of wood to be in kind with the structure, but we are covering up the structure with a mitigating panel. Sound transmission. So sound transmission is a function of weight, and one of the great benefits of building with wood is it's lightweight. One of the great drawbacks is it's lightweight. Because it's lightweight, it doesn't mitigate sound transmission in the same way, and when it doesn't do it adequately. So generally, we're pouring concrete toppings on top of wood floors simply to add mass to manage sound transmission. Shrinkage is a problem with wood. So wood is it's a natural material, and trees require water to grow, and they are full of water. And when they're harvested, they first dry, and they'll lose 50% of their mass is just loose water within the wood, and then they'll further lose 25% of their mass, which is water stored in the cell walls, and that's the process of curing. When we lose the mass and lose the water, we shrink. Wood will generally shrink. Anecdotally, we think about 2% perpendicular to grain and 0.1% parallel to grain. So if you think of wood as like a bundle of straws, as you take the water out, the bundle of straws collapses, and that's the perpendicular to grain shrinkage. The length of the straw doesn't change really. So 0.1% parallel to grain and about 2% perpendicular to grain. If we're that simple, it'd be easy enough to deal with. It's not that simple. Annular shrinkage, that's the shrinkage around the annular ring, is something like 50% higher than the radial shrinkage. So I said 2% perpendicular to grain. Well, that really means 1.2% radially and 2% annular. And that's what causes wood to do this. It causes it to cup. On this surface, it was the grain was more dominated by the annular orientation relative to this surface, which is more dominated by the radial, and therefore it cups. And so we get cupping and twisting and this kind of bulging effect, just depending on where we cut the piece of wood from the tree. The amount that wood shrinks, it's a building movement. All buildings move. The shrinkage in wood is comparable to the other kinds of building movements. So to put it in perspective, concrete, when it shrinks due to curing, also shrinks about 0.1%. So about similar amount to to the amount that wood shrinks parallel to grain. And that's why we wind up with cracks in our concrete. A steel beam, midspan of a steel beam will span over 360, probably around 20 millimeters. Well, that's the equivalent of shrinkage over 3 floors of a wood building or something. So we're used to dealing with movements in that magnitude, and the solutions are similar. It's providing slip joints and expansion joints and other types of things. Another consideration with wood framing is mass timber framing is beam shadows. In a concrete building, the kind of prototypical concrete building that we're seeing in Toronto these days is raised floor, surfaces under the floor, exposed concrete ceiling, flat slab with drop panels. The innovative slab developed by Dermot Sweeney has tapered drop panels, and all of these things allow maximum light penetration. There aren't a lot of features on the underside of the ceiling to impede the penetration of light. As soon as we start building with beams, we start introducing beam shadows. So this image was these KPMB's old offices on King Street, and we were involved in a competition with them for a mass timber building, and we were talking about structural systems. And we just looked up and saw, like, you can see dramatically less light on the second bay than the first bay, and it got darker and darker the farther away you get from the window. So we've got to be sensitive to beam shadows in wood buildings in a way that we don't in concrete buildings because it's flat slabs, and in steel buildings because we have ceilings. I mean, we don't expose steel in multi-story buildings because it needs fire protection. And this, of course, is what we would all like to see. This is the Villa Madeira by Alvar Aalto. Incredibly, this is not a mass timber ceiling, of course. This is just a wood ceiling. But without the beams, the light penetration is amazing. So, we're hearing a lot about it these days. Is it new? Well, of course it's not. I mean, we've been building with mass timber or heavy timber for centuries. This is the Google offices in Waterloo by Robertson Simmons Architects, repurposing an existing heavy timber building. Blackwell's been doing it for a long time. The Grand River Recreation Center by McLennan Young Combs Miller. It was just McLennan Architects at the time. This would have been the late 80s. So Blue Lamp Arch and heavy timber deck. Milton Leisure Center is another example from the early 90s. Again, McLennan Architects, which was glue lamp beams and purlins and a heavy timber deck. Jackson Triggs Winery by KPMB. This was another late 90s project that I think stands up today. It's if this would be celebrated today, 20 years later, as an architectural achievement. Cawthra Community Center, Diamond Schmidt. This was another one of our projects. Bird Studies Canada headquarters. I love this project. I don't have nearly enough photos of it, and I've got to do something about that. And to the point where you can see that this photo was scanned out of a magazine, like out of a physical magazine. I love this because this was done by Montgomery and Sizem in early 2000 or maybe in the 90s, late 90s. But it is an archetypal building now. It's a steel frame with heavy timber deck. Customs and Immigrations Plaza in Fort Erie Peace Bridge by Knorr with Blackwell. And Moreland's Cab Dining Hall. So this is heavy timber mixed with, or mass timber. This is glue lam trusses mixed with light wood frame. And the French River Visitor Center by our beloved Barry Sampson. Niagara Credit Union with Philip Beasley Architect. So these are the projects that I was referring to earlier, where where wood, because it's chosen for its aesthetics and detailed to be expressive, is often twice as much as the utilitarian comparable. Malvern Library, Kingsland Architect. And the Fielding Library was super cool. I'm going to just take a moment to say that unlike other materials, wood, the cost of the fiber in wood is 2/3 of the cost of the structure in wood, which means that material really drives the decision making in wood. And the volume of fiber in the deck is the highest, the greatest amount of fiber in wood is in the deck. So even though the beams are the expensive elements, they represent a much smaller quantity of material than the deck. So on the Fielding Winery, as was the Jackson Triggs Winery, we chose to use corrugated metal deck because it was dramatically less expensive and allowed us to keep the wood in as the exposed structure. Another nice little interesting radial project with Phil Carter. In Lakeville College School, Diamond Smith. So here's the big lesson. This is a steel frame, wood purlins and deck. We blew our brains out detailing a structure that was so incredibly light and expressive.
I spent my weekends for 3 months fiddling with this model back because it was before software could handle a lot of the cut. So you remember you have to move your mouse over to this side. They can't see it on the screen. I don't know how long you've been doing that. It was back before software could handle kind of the analysis process that we were looking at doing, and trying to find the iterative process of this. This in St. Catharines, which you might not have in this because it's kind of a combination of all materials, but kind of detailing these trusses. And sorry, I cut you off, but I know where you were going. All of the work we did, and you can't even see it.
You can't see it because there are these frames for hanging basketball nets. There's sprinkler pipes. By the time you get the other junk up there, this extraordinarily light filigree of structure is completely invisible.
We wanted those rods. You can't see. We wanted these rods and these cables to be slightly bigger, and all of our kind of analysis problems would go away. Like cut the engineering time in half almost. And fair enough, they were adamant that it had to be reduced and refined, and so we did it, and we learned a lot, but then it's gone, it's disappeared and irrelevant compared to the rest.
Innisfil Rec Center, this again has become an archetypal project where the major elements are steel, but as much wood as we can use for durability, if not purely for aesthetics. This is the St. Catharines Aquatic Center that Shannon was making reference to. So maximize the use of wood, introduce steel elements in here to stretch the span beyond what would be otherwise achievable in wood. And then for the volume of fiber award, we go to the Scarborough Library. How much wood could we squeeze into one project? All right, extraordinary project. A lot of wood. CFB board and dining facility. This is worth talking about because it really gives you a sense of the range of form that's possible in wood. So in steel, it's difficult to build an arch. You've got to curve big steel members. It takes extremely heavy equipment. or you've got to cut things out of plate. It's a real challenge. In concrete, building complicated forms is expensive. In wood, you don't get a curved glue lam for free, but generally it's about the same process as making a straight a straight glue lam beam. So it's not a gigantic burden to make a curved glue lam. A lovely little project with C.Y. Lee. The really interesting thing about this one is the pre-stressed tensile roof and the fact that it was taken out of a single plane and made it a space-occupying truss over multiple bays. And then my partner Christian really took it to another level of refinement with the Redstone winery. This is CLT panels with a king post. My partner Ian, Indigenous Learning Center at Laurentian University, the Diamond and Schmidt architects. And my partner in Corey's project, the Iroquois Longhouse with Brooke McElroy. And another one of Christian's projects is the Ontario Place Waterfront Park. In this case, we can see the CLT panels used almost vertical like beams, as well as not just acting as a deck. One of our first multi-story buildings is St. Jacob's Farmers Market in Waterloo. So multi-story, glue lam, CLT floors. And this is one of my favorites. This is the Nike Crystal Coliseum. This was a building that was built only for a weekend, I think, during the Toronto Marathon, and it was several years ago. But this is a floating building on a barge. Glue lam structure with fabric roof. We designed the glue lam and the fabric. And so effective because the fabric is translucent, so it acted as a beacon at night with the lights glowing through, but also reduced the daylighting requirements. This was possible because there needn't be an envelope. It was a temporary building, so it didn't need any insulation at all. A wonderful thing about this as a system is that if water gets through that membrane, you see it, and it dries up. It's not like so many of the wood systems. If you have a multi-layer assembly, water gets in there, you don't even know you have a leak, and so you don't address the leak, and that's the thing that accelerates the deterioration of a building. But if you just have a single layer, then water comes through and it drips on the floor. You put a bucket under it, and then you go fix it. Expanding on that, this is the City of St. Louis Park Arena in St. Louis Park outside of Minneapolis, Minnesota. And this is an NHL-sized rink covered with a glue lam and fabric roof. This is one that we did a couple of years ago that was really extraordinary. Now we were involved because of our fabric expertise. It happened that we were able to assist the base building engineer in the wood as well. But I'm going to confess that I find that the detailing of the wood here is just a little bit clunky. But as a project, it was so effective. So what other things can we do? We've got beams and girders are the obvious thing. Let's look at some of the systems. So these images I developed for an article that I wrote for Canadian Architect earlier this year called the Mass Timber Primer, and these images have been popping up everywhere. The number of ways to build. This is the kind of the simplest default is long beam, short deck. So if you have an asymmetric bay, orient your beam in the long direction, your deck in the short direction. This is not what we would do if we were designing Walmart, for example. In a Walmart, we would orient the heavily loaded elements in the short direction and the lightly loaded elements in the long direction. So naturally, if you don't have as much load, it's easier to span farther. But as I mentioned in wood, the cost of the fiber dominates the cost of the system. and the deck is the bulk of the fiber. And so we want to minimize the deck span. Gary Williams, who owns Timber System, he once told me that the system with the most economical deck is the most economical system. So we orient the beam in the long direction because the beam has depth and so it can be efficient. We orient the deck in the short direction because that minimizes the amount of fiber in the system. Alternative, short beam, long deck. So just the opposite to what I was saying. Why would we ever do this, having just told you that the other is the best? We would do this if depth of floor was important to us. So we have a thicker deck, but it might be 50 millimeters thick, but we might save 200 millimeters in the depth of our beam or something like that. So, and in commercial development, especially in an urban context, floor-to-floor heights are critical, and squeezing a few inches out of the floor-to-floor height is important. So we might orient the deck in the long direction. Beams and girders. So if we say that the system with the thinnest deck is the most economical system, then what we want to do is we want to choose the thinnest deck that meets our basic criteria, probably based on fire rating, and we want to span that as far as we can, and as soon as we hit the limit of the span, we put a beam, and we put another beam, and we put another beam. We don't want to put columns at that short spacing. We don't want our column spacing to be governed by our thinnest deck, so we end up introducing girders. So in this particular example, you can see we've got the deck as thin as it can be on beams spaced just far enough to, or just close enough to accommodate the maximum span of the deck, and then we use a girder to negotiate between the beam spacing and the column spacing. A two-way beam system. So one thing you might have noticed is that in the previous system, so I'm going to back up a slide here, beam and girder system, there is a hierarchy. There is a hierarchy of deck, beam, girder, which imposes an orientation on the space. So there's a hierarchy of views and of circulation, and it starts to have an impact on mechanical distribution, all of which may be fine, but may not be fine. And it's also optimal to asymmetric bays. So we would naturally want one bay shorter than the other bay. And most wood systems are optimal with an asymmetric bay, 1 to 1.5, something like that. So what if we want our space to be more democratic than that? We don't want to introduce a hierarchy, and we want column spacing the same in both directions. We don't want a 5x7 grid, we want a 6x6 grid. Well, one choice we have is to do a two-way beam system. In order to benefit from the two-way beams, we need to load beams in both directions. And so we might flip the deck and orient it in different directions in sort of a parquet flooring style or a basket weave style. And what that does for us is, in this condition, this beam gets exactly the same amount of load as that beam. And so all our beams are the same size. Another example is a two-way point supported CLT. So this is the scheme that was used for Brock Commons. This is the 18-story student residence at UBC. Tremendously innovative. You can see that there are no beams. Having a system with no beams is hugely beneficial from a floor-to-floor height point of view, from a mechanical distribution point of view, from a penetration of natural light point of view. So huge benefits to point-supported CLT. However, CLT is only made in 2.4 to 3 meter widths. And if your panel is limited to 2.4 or 3 meters, then that becomes the spacing of your column. So very, very tight column spacing in point-supported CLT buildings, which lends itself well to projects like student residences or hotels or or things like that, where you've got closely spaced demising walls anyway. Not an appropriate system for an open concept commercial office building. Threw this in. I don't know whether to believe this or not. This is a bit like believing in unicorns, I think. There's a European company that has developed an adhesive that will apparently allow you to block glue full strength parallel to grain, butt glue, full strength parallel to grain. If that's the case, and I have no reason to believe that it's not, except that it's too good to be true. But this would be a tremendous benefit for two-way floor systems, because that now could be an adhesive joint. I'm going to be preparing a lecture shortly on shallow floor systems, simply because for commercial development it's so important. But this would be one of the shallow floor systems that I would talk about, wide flat beams. So we know that deeper is cheaper is the kind of adage in structures. An efficient beam in bending is narrow and deep. The reason we would do a wide flat beam is simply to make it shallower. If we make it shallower, we have to make it wider. Using CLT, we can make very wide beams. So we can use wide flat beams to develop a shallow system. Look at the way it's detailed up here. We can see that the panel goes all the way to the midspan of the beam. If you have a beam that is as wide as a third of your column to column span, that doesn't mean your deck can be shorter, because if you start loading the edge of your beam, it's like a teeter-totter. So the deck needs to come over and bear its load right along the center line of that beam, so that the beam doesn't topple. So you don't save, the wide flat beam doesn't save anything in deck, but it does make the beam shallower, and that's good. The other thing is it reduces the exposed surface. In a wide flat beam, you expose the bottom and the two sides to fire, whereas a deep beam, you expose the two vertical sides and the bottom. The deep beam will be much more affected by fire than the shallow beam. So what we want to do is minimize the amount of surface, and a wide flat beam will do that. So our fire load case is likely to be better in a wide flat beam situation. Another one that we have not done, but we were advocating for a project, and we will do it eventually, I'm sure, is wide flat beams on top. The deck is unaffected. The deck has to span to the middle of the beam regardless, one way or the other. But if we put the wide flat beam on top, it means we have a featureless soffit, and that's beneficial for the reasons that I was talking about before, for mechanical distribution, for space planning, for light penetration. There's a number of reasons why that's better. It does mean you have to build up your floor, but in a lot of projects you would build up your floor anyway. So what about wide flat beams flush? Well, I already told you that if you load the edge of your beam, then your beam is vulnerable to toppling. So if you want to do wide flat beams flush, what you need to do is use a wide column. Your column has to be nearly as wide as the beam itself, so that when the deck loads the edge of the beam, it doesn't make the beam simply topple over. That's not to say that it's not a good system. This is what is being, a similar system is what's being done for George Brown College, the Arbor, with our good pals Fast and F from Vancouver. Very, very clever structure. But these long columns they had to make a concession to the columns in order to get it to work. There are a number of double beam systems around. Double beam systems are really interesting for a number of reasons. One is that in glulam, you're limited to about 365 millimeters in width. So you're going to run out of size if you start getting into large beams. You just run out of available size. And so having two beams, you get, twice the width, obviously. The double beam allows the column to go up between them. So why is that important? Well, I told you that wood shrinks about a 2% perpendicular to grain and 0.1% parallel to grain. If we have a 600 millimeter deep beam, that beam is going to shrink 12 millimeters as it seasons. Now, all of these things, you're going to buy, if you buy glulam that's already seasoned, then most of that shrinkage has already happened, and so maybe it's 6 millimeters instead of 12 millimeters. But regardless, the shrinkage is significant. If the column goes in between and supports the column above, now the floor-to-floor shrinkage is only the shrinkage parallel to the grain of that column. If you stack it or platform frame it, then you have the floor-to-floor shrinkage is the shrinkage of the beam plus the shrinkage of the column. And that adds up over multiple stories of building. So there's a real benefit to having the column sneak up between and having a beam held off on either side with a hanger. This is a really interesting, this is one of the concepts for the Trinity residence which we're working on right now with Meccano. This is cruciform columns with a double beam. The cruciform is seen by some people as a frivolous and in fact is probably being value engineered out. But the cruciform is essentially just a shoulder for the beam to sit on, to transfer load into the central beam, or central column, and you can see the central one slips up in between. So in fact, it's a really, really clever way of building these columns, and I think that it was probably short-sighted to think that they could be value engineered out. I don't know that it's actually going to be a value add to take out the cruciform. I think they were really, really super clever. Triple beam system. The triple beam is this was developed by my colleague Simon Raymond in my office for a project. It has a number of really interesting enhancements. In the triple beam system, the outer beams can run continuous past the column. The column is notched and runs up through in between the outer beams, and the inner beam is discontinuous at each column because the column has to slip up through, of course, to manage the shrinkage. What that means is that we have moment continuity at every span, and if you look at your beam design tables, you can see that a continuous beam that has moment continuity at the columns is dramatically stiffer than a beam that is discontinuous at the columns. That is, that this shape is much better than this shape. And so this is a really clever innovation. The other advantage of this over a two-beam system is that we don't have a surface in between. So we've reduced the amount of unprotected surface from fire, which allows us to make the beam smaller as well. In this particular case, what Simon did is he made the central beam deeper since the outer beams can carry the deck. So took advantage of a little bit of extra depth as well. Staggered deck system. This was developed by Equilibrium with Michael Green for one of Michael's projects. And it is a really clever way of achieving long spans with thin decks. So you're essentially making like corrugated cardboard or corrugated roofing out of wood. You get the You get the flexural benefit of the full double depth, whereas the volume of timber is essentially the volume of the single. VCTC, or voided concrete timber composite. We were trying to get out of the habit of referring to this as bubble lam, because bubble lam automatically has a connection to bubble deck, and yet the voids don't have to be. So VCTC is a timber panel with a thick composite deck on top, comparable in thickness to the timber panel. So one might have a 250 millimeter timber panel with a 250 millimeter deck and 200 millimeter voiding balls. So what are the benefits of a system like, do I have a, yeah, so here is the assembly up close. Some models of it that I built. What are the advantages of this? Well, first of all, we can span far. So the concrete allows the wood to span farther than the wood otherwise would have. The wood allows the concrete to span farther than it otherwise would have. So whether you look at it as an enhancement on a concrete system or an enhancement on a wood system, it doesn't matter. The two are better than either one of them from a span point of view. From a loading point of view, we can tune the thickness of the topping to do whatever we need. So in a traditional wood concrete composite, we would do thick wood, thin concrete topping would be the optimal, and your capacity, your strength is limited by the strength of the wood. If we do something like this, we can say, as soon as at 286 millimeter, we've run out of depth. We can't make a panel deeper than that reasonably. But we can have a 600 millimeter slab on top of that. So it sounds like, well, what's the point of doing the wood if you've got 600 millimeters of concrete? Well, you'd only do that over the atrium or over the auditorium or something. So you know, in an academic building, or there are buildings that have a flexible spaces. So you optimize the system for your typical bay. And something like this will accommodate all your atypical conditions. It can handle very heavy loads. You could have a transfer column, for example. You make your concrete thicker. You can have a transfer slab, even though that it's a wood and timber building. Whereas a traditional timber building, as soon as you have an atypical condition that exceeds the limits of the timber, you have to go to a different system. You go to concrete, you go to steel, locally to deal with the anomalous condition. Whereas something like this, it's the same system. Different, you tune the balance of concrete to wood, but it's the same system. The other major benefit of something like this is that because the concrete is thick, we can put a wide, flat concrete beam within the thickness of the topping. So it doesn't really look like it here. It looks like equal spans, but in fact, this is intended to illustrate a situation with a 6 meter span in this direction and a 9 meter span in this direction. In the direction parallel to the surface wood grain, where the panel is strong, the wood and the concrete are acting composite. So we have a composite system, wood and concrete, to stretch the ability of the concrete to span. The concrete that would have spanned 6 meters now spans 9 because of the wood. In the direction perpendicular to the wood fiber and perpendicular to the joints, because remember we can't transfer moment through a joint, we just have a wide flat concrete beam that's built into the topping. What that does allows us to do a featureless soffit. So now we've got a system that can approach the thickness of a concrete flat slab. So we can keep things much shallower. Minimizes the surface area for, like, you can't get less surface area than a flat surface from a fire point of view. So it's very fire effective. We can achieve even greater fire effectiveness by putting extra bars in the slab. So in the event that the wood burns away completely, we maintain integrity in the concrete if need be. The voiding balls, these are plastic balls, HDPE plastic, recycled plastic. They're there for two reasons. One is to displace concrete, because the less concrete, the less weight, the less cement, the less sand. So displacing concrete is a good thing. Also, it encapsulates problematic plastics into our building for a long duration. That's just a secondary benefit. But the system would work just as well without them. Like, it's just a thick topping on thick concrete would work perfectly well. It's just it would be 30% heavier, and so why would you bother? This is the Pico Delta beam. So it's called a delta beam because of the shape of the beam. I think that the original designers conceived it as a triangular beam with a wide flange. It's now kind of hat-shaped, but the hat-shaped beam, it does the same thing. So it's a tubular section with a wide flange. The wood can sit on the bottom flange. The wood is made composite, so we pour a concrete topping on top, which allows this to be a long span. The sides, the webs of the tube, are perforated with holes all the way along, which allows, when the concrete is placed, it allows the hollow beam to fill with concrete. Inside the beam there are rebar, so that the rebar are contributing to the strength of the beam. The great benefit is that while the soffit, that bottom flange plate, is not protected from fire, it's fully effective in normal service loads. In the fire load case, we can neglect it because we have rebar inside of the concrete, which has filled the beam. So this is the system we're using for 77 Wade, and it's a tremendous system for long span shallow floors. This is a fanciful system that we developed. We were trying to think of how do we span long way. How do we have a long span two-way system all in mass timber? And so we came up with this stressed skin lattice. We have mass timber panels on top and bottom, oriented in opposite directions, and then in between we have wide flat glulam beams oriented in opposite directions. So that in one direction, in this direction, we have a composite system with a wide flat beam and a mass timber panel as chords, and the web is made up, it's like a Varendale truss, the web is made up out of these perpendicular glulams, and in this direction it's the opposite. So both directions are equally effective and can achieve long spans in both directions with all mass timber. So here's your cross section showing you the Varendale truss. To remind you that a Varendale truss is a truss without diagonals, where the shear is transferred through a vertical element only, which is why the vertical elements in Varendale trusses are wide. This is a reciprocal frame. Reciprocal frames are kind of, I did a lecture on reciprocal frames first 10 years ago maybe, and I did it because it was fun. And I love lamella structures like the Fort York Armory. I think they're really beautiful and clever. But in fact, as I have reciprocal frames in the back of my mind, I keep coming across places where a reciprocal frame is actually a very useful thing. A reciprocal frame in a democratic two-way system with equal spans in both directions in mass timber is very effective as a way of reducing our deck span. They're a bit of a pain in the neck because they have to be shored until they're built. So, no element is stable until all the elements are there. But they are quite effective. This was an orthogonal reciprocal frame. This would be the lamella. This would be similar to the Fort York Armory or lamella structure built by Frederick Zollinger in Germany after the First World War. So people associate these with the vault. And to be sure, if you want a long span, the vault helps an awful lot. But there isn't a magic distinction. The reciprocal frame doesn't require the vault. This is a bending, stiff, two-way system made up out of short elements that are only transferring shear. This is one that's been tickling my back and my brain for a decade or more. This is the Palace of Labor by Nervi. Just an extraordinary project with concrete beams that follow the lines of principal stress. I thought, why can't we do that in wood? And we can, of course. It actually lends itself quite well. So we can use a combination of straight and curved glulam beams, because it's no problem curving a glulam beam. Even glulam curving in plan is possible. And then we have ring beams here. The function of the ring beam being nothing more than keeping this curved beam from rotating. You know, if you curve a beam in plan, it just wants to topple over. If you can prevent it from rotating, it actually contributes to supporting load. The nice thing about this system is that it doesn't matter what kilogram of load you are. You get to a beam, you go straight to the column. There's no hierarchy. You don't get on a deck, go over to a beam, go over to a girder, go back to a column. Wherever you are, your load is going straight to a column. And so in that respect, it's very effective. This is a cassette force system. Imagine we make a box, glulam side webs, CLT top and bottom cord. We make a box. We can span a cassette a very long direction, and this is what they've been developed for. The lignature system from Europe is super clever. It's taken the cassette one step farther and incorporated acoustic mitigation. So within the box, there is sand or lean concrete for mass, for acoustic sound transmission. There's also this second layer that's filled with a Roxel insulation or an acoustic insulation, and then the bottom surface is perforated. So that what this does, it gives the mass timber panel great sound absorption qualities. This is another proprietary system, Cree by Romberg, which is a combination of mass timber and precast concrete. This is not a mass timber system, and nor is it prefabricated. I just love it, and if you can look it up and see some images, this is the Kung Holzbau system. It's essentially two-way layered 2x elements, light wood frame. It's all filled with sand in between. So you get tremendous two-way capacity out of the system and throughout, but it does not lend itself to mass fabrication. It's probably very slow to build. God knows whether this actually will develop legs, but it's so cool that I wanted to share it. Here's a close-up view of the system. One of the benefits of mass timber systems is
You have a meeting at 1, right?
Yeah. What time is it?
5:02.
Okay.
And you're not 5 minutes from done.
Oh, I must be, no? I'm almost
You're on slide 83 of 117.
Oh my God. Okay, I gotta pick up my pace.
Or you can finish recording it after you're.
Well, I'm not sure. Like, I'm almost through the floor system, so I don't remember what you're talking
pictures of
about.
buildings. I could borrow.
Yeah.
But I don't know all of them, because some of it is past my time at Blackwell. But
Yeah.
certainly talk about it a bit. So finish these systems.
Yeah, I'll finish the systems. I'm not going to elaborate much on the buildings anyway.
I'll show them pretty pictures.
Yeah.
I can do
Sure.
that.
You are a pretty picture. One of the benefits of building in mass timber is the ability for mass custom fabrication. because these things are built on 6-axis milling machines. They're very tight, like 1/10 of a millimeter tolerance. So one thing we looked at doing is a CLT shell. So this is a lost form system. We're just using the CLT to generate a shell, which then allows concrete to be optimized in its thickness. So we minimize the concrete by giving it an optimal kind of arching form underneath using CLT. Do the same thing with NLT. So one of the things about NLT is you can create any ruled surface with NLT or DLT, any ruled surface. So depending on how you set up your boundary conditions, you can create a vault or you can create a hyperbolic paraboloid simply by orienting your boundaries at an angle relative to each other. You automatically create a hyperbolic paraboloid. A hyperbolic paraboloid, if that is what is describing the bottom of your slab, optimizes the shape of the slab. And so again, we can minimize concrete. In this particular case, again, it's a leave-in form system. We're not getting a structural benefit other than form creation, but we can incorporate our acoustic mitigation into our NLT. We can mill the boards, incorporate an acoustic barrier. So we do get that benefit as well. Here's a high bar NLT. This is a high bar NLT where we're actually taking the panels full span, and because of that, we can make them composite. So you can see that we have a line of columns here, and we have a line of columns here, and our NLT is continuous from column line to column line, so we can make it composite. In this particular system, it means that the columns have to stagger from one bay to the other. You can see that this column doesn't line up with that column. It lines up with the midpoint between those two columns. So God knows, maybe this is an idea for a pavilion and not a building, but it's interesting regardless. So this is, I thought I'd share the impact of fire, because fire will determine the most economical system. You know, we're used to with concrete, we design it in concrete, we add a little bit of cover, we get a fire rating, and we're done. With steel, we design it in steel, we protect it for fire, we're done. With wood, we'll design it, we design it one way, we add the dimension or we'll optimize the system when we add the additional timber we need to resist fire. The system we chose to begin with is no longer the optimal system. So what we can see here is, let's just look at two of them. You can study that. I have no doubt you're going to study this diagram on your own. But beams and girders with CLT deck, so that would be this one here, is almost the optimal system from a volume of wood fiber without a fire, in the absence of a fire. After 2 hours, though, the voided concrete timber composite is dramatically better from a volume of fiber point of view. So if we design the same system for a 2-hour rating, optimize the two systems for a 2-hour rating, after 2 hours, this one is less wood fiber, whereas at 0 hours, this one is less wood fiber. Here's another little diagram that's interesting. This is fiber volume versus aspect ratio. So aspect ratio, 9x9 bay is an aspect ratio of 1. And so this is a beam and girder or beam and deck system. As we go up to an aspect ratio of 2, you can see we've saved about 15% on the 15 to 20% on the volume of timber. This is with a fixed bay size in the sense that it says 50 square meters. So it might be 5x10, it might be 7x7, but it's 50 square meters. And varied the aspect ratio and did the design and found that the longer aspect ratios are giving us less timber. Now remember that I said that fiber volume dominates the cost of timber systems, and that the premium on a timber system is roughly 15%. If we can take 15 or 20% of the fiber volume out simply by using an asymmetric bay, we can recover the premium of using mass timber. Some of the panels available: glue laminated versus cross laminated versus nail laminated or dowel laminated. I'm going to very unfairly let Shannon cover this one.
What? Like your connections or your column height?
This is the columns.
Frack, I know nothing about the high-rise column design.
My point was going to be that we want to start building tall. Columns start becoming the driver. We're doing an 8-story lab building right now, and these are the kind of solutions we're looking at for columns. So we just the columns wind up getting very big and using up an awful lot of real estate, and so we're very often into strengthening columns by putting steel cores in them, either wide flange or hollow steel.
Did you look at the slide already that said how tall can we build with glue lam columns? Yeah, hint, not too tall.
Yeah.
That is not the same as how tall can we build with wood, because that is, as of yet, unlimited.
That's right.
Because there is very much a question like that. I realized that I didn't know this slide was in here. This appeared on me, and it makes it sound like my question was a trick question. It is not.
Yeah.
It's unlimited as long as you apply for alternate methods for design. The columns we need to work on, but that doesn't mean we can't build tall with wood.
But it's not cheating to reinforce your column with steel any more than it's cheating to reinforce a concrete column with rebar. Right?
Exactly, it's the same thing, and flitch beam is still a wood beam with steel embedded in it. Yeah.
Thank you, Shannon.
Thank you, Dave. So I've been doing chores and Christmas decorating. I didn't expect to be doing any of his timber lectures. So I haven't even looked at these slides, so I don't know what's coming up. We'll wing it. And like I said, they're mostly Blackwell projects, and I haven't, as much as I dabble in Blackwell projects periodically, I haven't been there in a long time. So what does he have here? Typical column bay, 5x5, interior column, 4.4 kPa. I'm not quite sure why it would be 4.4 dead kPa, 2.4 live because it's an office. High dead loads. So here were the different designs that worked is what I am taking out of that. I don't know what these ratios are. That must be the volume of wood and then the dimensions, but I don't quite know how they relate to each other. But basically, the wood we need to reinforce with something is what I'm assuming his takeaway here is. So let's go on to the next slide. And then how do you connect? How do you connect these things? Because we're connecting large things, maybe we're doing unique things. So this is a way that helps, I'm assuming, deal with the connection. This eliminates the need to try to connect multiple beams coming into a column with a floor plate on top of it. Wood is excellent in bearing. We like to bear things with wood. So this allows us, rather than to try to connect in shear at the end grain of it, we're connecting along the side to this column and then supporting this beam in bearing on the top. In fact, Dave and I build our decks this way rather than try to have one layer of framing with deck boards on top. Dave and I do a 4x4 grid at 5 feet on center, and then we do a 4x4 grid at 2.5 feet on center, and then we do 2x6 deck material on top of that. So stacking them as we go up. And our actual deck roof is actually built in this style too, where we laminated our beams on the side, and then did laminated beams on the top. It's interesting that if they're doing this, they didn't laminate on both sides. I'm not quite sure what the goal is there. So here's where we get into the difficulties with built-up columns. We're trying to connect. We need the load to actually make it to the steel. If you just connect it to the wood on the side, how does that load actually get into the steel element? Because as much as the deck passes over the column, it's not the one carrying the majority of the load. The majority of the load is actually the beams. So we've got to actually get that load into the column somehow. How do we manage load, transfer, ductility, fire, and shrinkage all at once? I have no friggin' clue. So let's look at the slides and maybe I can infer it. Okay, so we have a few things happening here. This is embedded, slotted into it. So we're dealing with our load transferring into the column and bearing. I said that's a great way to get load into a column. We have a hidden knife plate connection here. Steel is crap in fire, and if that is the thing that's getting all of our load into our wood, and we don't want to have to fire protect things, we don't want to have to come in and drywall around this connection for any of the bits that might be exposed, we're actually, I'm assuming, using the wood as the fire protection for the steel, the same way we would concrete around steel, which is exactly what we do for reinforcing in concrete. So I have never seen this slide before. So this, we slot this in here, we dowel through, so again, we're using the wood as the protector. So what things did he say he was trying to solve? So load transfer in bearing, fire by the fact that it's protected by the wood. Shrinkage, it looks like we're dealing with the fact that the wood does, or the steel does all the transferring of the load, so we don't have an interface of wood to wood. So even if the wood shrinks, we've got dowels here, so there's continued, like it can have small adjustments. If there's shrinkage in this direction, the steel just moves with it and takes the rest along for the ride. The last one, ductility. Ductility is what we like to do for seismic design, and this connection right here being a steel connection, I'm not sure what the thought process was for the design, but I'm assuming they've treated this like their ductile hinge, or a place that in a high seismic load, as much as the wood is brittle, we use the steel for all the ductility. The difficulty with using anything ductility as a seismic kind of capacity mechanism is that you're actually designing an upper and lower bound. You don't actually design it to be too stiff. If it's too stiff, it won't yield and you don't get the benefit of the ductility. So this is highly fine-tuned to, at the seismic load, become ductile and actually yield. We want yielding to happen because as it yields, it allows the building to move, which absorbs energy, which actually reduces the seismic loads we apply to the building. So it's a highly fine-tuned process just for ductile connections. And then we're adding in fire protection, shrinkage, and load transfer in a bearing condition. So these steel connections become a very kind of refined approach in the design that, yeah, we have some of that in steel, but a lot of the times we just hide it and it kind of goes away. The ductility problem is real, but not that much here in Toronto. And steel has the added benefit that the entire building is ductile. In a wood building, it becomes slightly more considered because this is the only place where we can get our ductility. Column beam girder connection detail. Okay. So this is slotted over the top so that we have bearing connection on this column. Both of these beams and girders come in on the side that have a bearing plate for bearing, bolts fitted into it to deal with the eccentricity and the load. Strapping, steel seismic beam hanger. Okay, so this is helping deal with yielding at the connection. And then this is a slotted pipe that allows this column to be placed so it can't move and shift, but it allows some difference in up and down movement so that it's not locked in place for shrinkage. Here the steel, they actually kept the column off of the wood and off the CLT panel, so there was some ability for tolerance there as well. Glulam column. So you can see earthquake wasn't as difficult for this one, I'm assuming, or maybe it was, yeah, Brock Commons. So it depends on what their ductile factors were for this. These screws have kind of been revolutionary. I've not seen these connectors before, but that looks fantastic because it changes the angles of them. This would help you template exactly where your screws need to be, which is actually kind of brilliant. You've got a connector on each side, and then the wood slots down onto it. So you screw into each end, and then you slot on, and you've got a lovely hidden connection. So, show us some sweet mass timber projects. Okay. This one's a built project. Brooke McElroy and Blackwell did it. It had to meet the heritage requirements of downtown Toronto, so the facade had to be, your regular brick building look for the vibe of it. But here's what was happening inside the building. You've got glulam columns, glulam beams, CLT panels. You can see the hidden knife plate connectors for the columns, and these ones, they're not completely hidden connectors, but you can see that they've got these slotted down around, similar to that detail that Dave showed us. And there would be a knife plate inside that as well that was screwed through the knife plate. And so here it is kind of in real life. 80 Atlantic, Quadrangle and RJC, Reed Jones Christopherson Engineering. So 4-story, 1, 2, 3, 4, 5-story CLT project. Distillery District with Shop Architects. High rise, or is it this one? Yeah, I guess it's the Ribbon Building. So you can see CLT, I'm assuming it's variegated here for acoustics. 35 Golden, or the Golden Nugget Building, mass timber construction. I don't know. Yeah, so here's a rendering of the inside. This one I thought was a Pico system, but maybe not. Again, I don't know all of these projects. TRCA headquarters, DTH in Blackwell. I know Dave worked a lot on this one, and it's been on hold for a while. This one really is what helped him develop the Infina product. That I always joke that it might be the only thing that ever makes us rich, unless we can manage to buy real estate somewhere. But really, the bubbles in the concrete on top of the mass timber flooring system, whether it's CLT or NLT, engineered systems. Really kind of that helped fuel this project. So you can see this one's actually the NLT. So this was the alternate submittal by ZAS and RJC. I think Blackwell won that. I think that was DTH won that one. I can't remember. 77 Wade Avenue, mass timber project. This one I can speak about a little bit. This is the academic tower with PATCOW and MJMA and Blackwell. So this is the one that I had originally designed the foundation for in 2012, or Mike Vindell, a principal at Blackwell, and I together, we were both associates at the time, designed a foundation for that project for an unanticipated or an unconceived tower. So we had to make up our own tower because there was no fee to design a tower, but they wanted to build the foundations at the same time they built the high performance sports foundations. So they built all of the foundations at once, and we had engineered a 16-story tower, but we had to anticipate where braced frames were going to be, everything, and we explained that it was going to limit kind of the future iterations that might happen for this project, and U of T was happy with that. And so then in 2017 it came back to life. And I did some of the preliminary analysis for this. The braces actually and the columns, like Dave said, start to be a really governing factor. The braces, especially considering buckling for wood, really came into play, whether it was a tension-only element or a tension compression element. So we worked really hard to detail that. And wood, we actually tried to keep out of tension if we could. So it was a fine balancing act of not having too much compressive load on it, but we also didn't want only tension ever. So there was iterations of like moving around these elements, and it changes what wood grade you use as well. The Laurentian building with Levitt Goodman and Blackwell, mass timber specialists. I love these two images. So you can see kind of the wood happening in the background here. So this was another competition with George Brown, the Arbor. PATCOW and MJMA partnered up with Blackwell. Again, I did a lot of the modeling for this project for the competition stage. Unfortunately, unsuccessful. This was the winning team, but I know it was a long, drawn-out process. I think both are absolutely lovely. This is the Brock Commons with Acton Austrian, Vast and App. So you can see glue lam. What's really nice is they have kind of prefabricated openings, able to deal with a lot of stuff off-site. And a tower in Norway. All kinds of wood projects kind of coming up. You know, Dave and I joke that Blackwell right now has 6 projects in the works that if they were built right now would be the tallest mass timber buildings in the world. But almost every firm could probably, or every firm that is a wood specialist could make that claim right now. This is obviously a dead project now since Sidewalk Labs has pulled out of Toronto, but these were some of the kind of preliminary renderings of the mass timber projects that they were anticipating. CAMH with KPMB, this is a project that's on the books. My understanding is that it's supposed to go ahead at some point. This one also uses the Infina system with the the bubbles in the concrete on top of a wood platform, kind of maximizing the benefits out of both materials, making both do more than they could have done independently. And just to show that we're not full of shit, you can build tall mass timber structures, and we've been able to do it for a very, very, very long time, for over 1,000 years. So this is just an example of a tall wood tower from the past. So I apologize for that disappointing finish on my part. I feel like Dave could have really sold that maybe a bit more than I could. But I'm glad I got to participate in it just a little bit. He's going to follow up with a glass lecture in the next few days, and then I'll be producing and probably filming the installations lecture. So that would be street furniture, playgrounds, art installations, all of the things that are kind of standalone but don't really follow normal building codes at all. And I'll also produce some slides for you for kind of veneer stuff. So look forward to the next lectures.